I will explain everything in detail. Please note down every step very carefully. My dear friends, I will explain biosensor application to the junctionless and charged plasma tunnel field effect transistor. But you can apply this application on your device such as MOSFET, SOI, silicon on insulator, FinFET, nanowire and TFET structure, etc. Earlier I had talked about TFET structure, how to design TFET in Silvaco in detail. Today I will talk about only on the junctionless tunnel field effect transistor and the charged plasma tunnel field effect transistor. There are two different techniques which can apply on the field effect transistor and tunnel field effect transistor. First technique is junctionless and the second technique is charged plasma, or we can say that dopingless tunnel field effect transistor. First we will talk about junctionless tunnel field effect transistor. The junctionless tunnel field effect transistor is a silicon channel heavily n-type doped junctionless field effect transistor which uses two different metal work functions to behave like a tunnel field effect transistor. One metal we are using at the source terminal to convert n-type to p-type, and the second work function I am using on the gate terminal. It does not have any metallurgical junction since the device has no concentration gradient in the lateral direction of the conduction layer, or we can say that horizontal direction of the conduction layer. It does not have any PN junction. It should be simple to fabricate and it has better electrical properties and less variability than MOSFET. Due to the absence of sharp doping gradient, it has better scalability and less short channel effect. Short channel effect like DIBL. DIBL is less in junctionless tunnel field effect transistor as compared to doped tunnel field effect transistor. Although the subthreshold slope of junctionless TFET is below 60 mV per decade at room temperature, but it has low on current and give poor ion-IF ratio. But by using different techniques such as stained silicon, dual material gate, etc., we can improve the on current of the device. This is the example of the junctionless field effect transistor in which we are using two metal gate at the gate terminal, in which we are using the two metal. One is at the source end and two is at the gate end. There is no need of connecting any metal work function at the drain terminal in case of junctionless TFET. Next is the charged plasma technique of TFET. The difference between the charged plasma technique and the junctionless technique is that in case of charged plasma technique, we are using the intrinsic doping at the channel region. It is approximate 10 raised to power 15, or we can say that 10 raised to power 10 according to the book. But in the Silvaco tool, I am using the intrinsic doping is approximate 10 raised to power 15. But in case of the junctionless tunnel field effect transistor, I am using high doping. It is approximate 10 raised to power 19 per centimeter cube. In the charged plasma concept, without the need of any doping, the P plus source side and the N plus drain side are induced in the intrinsic silicon body by choosing source drain metal electrode with suitable work function. High work function will induce hole in the source and the lower work function will induce electron in the drain. And the third point is absence of high doping concentration gradient leads to the simplification of fabrication process of the charged plasma TFET. There are two essential requirements of the charged plasma concept is as follows. Thickness of the silicon body must be less than the dB length. The formula of the dB length is epsilon s silicon Vt divided by Q plus 16 to n by the under root, where Vt is the threshold voltage, Q is the electronic charge, N is the substrate carrier concentration, and the epsilon is the dielectric constant of the silicon. Work function of the source drain metal electrode should be greater than or less than the psi I silicon electron affinity plus Eg by 2Q respectively. Source metal work function is 5.93 electron volt for platinum and the drain metal work function 3.9 electron volt for hafnium. For inducing the charge carrier approximate to the doped TFET structure, for example 10 raised to power 20 For in the source region, the platinum metal work function is required. For inducing approximate 5e5 10 raised to power 18 charge carrier in the drain region, 3.9 electron volt of hafnium metal electrode is required at the drain side. This is the structure for the charge plasma TFET. The difference in the structure of the junctionless TFET and the charge plasma TFET is that in case of the junctionless TFET, we are not using any work function at the drain side because we are using the high doping at the drain side in case of junctionless TFET. But in the case of the charge plasma TFET, we are using the intrinsic doping, so that we have to require a work function of 3.9 electron volt for inducing the charge carrier n type in the drain side. The other is same. We are using the gate work function is 4.5 electron volt and the source electrode work function is 5.93 electron volt. We cannot directly contact this metal work function with the silicon. We have to require the oxide layer in between them to avoid the silicide information. This is the structure of the charge plasma TFET. Next is the biosensor. A biosensor is an analytical device which can convert a biological response into an electrical signal and is used to provide rapid detection of the biomolecule. There are two types of biomolecule. First one is the neutral biomolecule and other is the charged biomolecule. In the neutral biomolecule detection, presence of the neutral biomolecule in the nano gap cavity is simulated by introducing material of different dielectric constant. And the charged biomolecule, the impact of charged biomolecule is simulated by considering positive or negative fixed oxide charge density at the Si-SiO2 interface. The biosensor can detect the presence of a specific biomolecule in a given target sample, such as human sample, urine, blood and saliva or food, and the environmental sample, water and the soil. For instance, a blood sugar detector non-invasively sense the presence of glucose in the blood sample. Detection or a recognition technique are of two types. Broadly, it will be classified into two types: label-based detection and the label-free detection. In the label-based detection, relies on the specific properties of labels or detecting a particular target. In contrast, label-free detection is suitable for the target molecule that are not labeled for the screening of the analytes which are not easy to tag. Label-free technique is another one increasing awareness of the novel techniques that do not require labeling of the ligand or the receptor. First, we will talk about label-based detection. The word label is represent to any foreign biomolecule linked chemically or temporarily to the recognize the desired analytes or biomolecule. During the biomolecule detection of the target biomolecule on sensor surface, the tagging is a mandatory step to be used in conjunction with biorecognition unit of to amplify the signal as well as increase the sensitivity of the biosensor. The labeling will lead to a more efficient detection of biomolecule as it enhances the number of binding sites. On the basis of labels, reagents such as enzyme, nanomaterials, quantum dot, and the dyes and the label-based detection can be categorized as fluorescence labeling, first one, second one is chem illuminance labeling, and the third one is the radioactive isotope labeling, fourth one is the electrochemically active probe labeling, and the fifth one is the nanoparticle labeling. In this presentation, we will talk about the label-free detection in detail because we are using the label-free detection in the FET-based biosensor. In order to reduce the complexity and evaluation cost, label-free method are proposed. The label-free recognition with no requirement of linking biomolecule. Examine the target biomolecule on the basis of physical or chemical attribute such as permittivity, mass of target biomolecule by observing and depending exclusively on binding sensitivity, selectivity and refractive index. Basically, the intrinsic physical property such as dielectric permittivity, mass, volume and conductivity indicates the presence or absence of the target biomolecule in the nanogap cavity. The elimination of confounding molecular labels has reduced the sample preparation time, procedure complexity, as well as analysis cost. The label-free biosensing has immense potential to be fabricated to micro-level system and provide better quality sensors that are highly flexible to remote diagnostic and field application. And it can screen any complex biomolecule with minimal assay development. Label-free method can be categorized as surface plasma resonance, first one, second one, quartz crystal microbalance, and the third one is the mass spectrometry, and the fourth one is micro cantilevers. This presentation mainly focuses on the recent development in the field of new label-free technique, for example, field effect transistor and other type of biosensor based on nanotechnology. Let's start with the FET based biosensor. Field effect transistor based biosensor are the suitable candidates from a variety of transducer in the label-free category. The first biosensor was investigated by Biefeld in 1970. The name is ion sensitive field effect transistor. Ion sensitive field effect transistor has good performance with charged biomolecule but poor performance for the neutral biomolecule, and it is also incompatible with the CMOS processor. That's why we are introducing dielectric modulated field effect transistor biosensor. In contrast, dielectric modulated field effect transistor devices are capable of detecting both charged as well as neutral biomolecule even in the small volume of sample with high detection sensitivity and the fast screening. Its working principle is related to the high responsiveness to the dielectric constant of biomolecule as well as charge effect. That is, charge carried by the biomolecule at the Si-SiO2 interface, such that on introducing negative charge biomolecule into the cavity, the charge effect dominates over dielectric constant effect in case of dielectric modulated FET biosensor sensitivity. There are few points about the nanogap you must know about these points. First is, what is nanogap? The gap in order of the nanometer formed between the two electrode or side of the gate electrode. It may be overlap or underlap of the gate metal. It is referred to as a nanogap in the biosensor. On the basis of the gap formation, the biosensing device can be categorized as planar nanogap device and the vertical nanogap device. The device with the planar nanogap, both the electrode were horizontally separated by 50 to 100 nanometer, formed using technique such as lithography, and are not capable of providing high throughput, and therefore it is less preferred. On the other side, the device with vertical nanogap, both electrodes are vertically separated in a perpendicular direction, formed using thin film deposition or wet etching process, has vertically suited electrode. The vertical nanogap devices are widely preferred due to their low cost, high sensitivity, more uniform electric field, and the controlled thickness. This is the structure of the vertical nanocavity. First structure is for when the air is present at the nanocavity, and the second structure is when the biomolecule is introduced or entered in the cavity region. This nanocavity is formed by the thin film deposition and the wet etching process. This vertical nanocavity structure is preferred. This vertical nanocavity structure is preferred due to their low cost and the high sensitivity and the high selectivity. Another point is the selection of the cavity length is a crucial factor as it affects the device parameter and the device sensitivity, drain current sensitivity, responsivity, electric field, and the transconductance of the proposed device. The nanocavities provide the efficient immobilization and are extremely sensitive since the nanomolecules such as DNA, protein, amino acid occupy reasonable percentage of volume in the cavity. To recognize the biomolecule, DNA, protein, amino acid, it must be in the reasonable percentage of volume in the nanocavity region. The biomolecule confined in the nanogap can modulate the electrical property at the device junction, such as impedance, resistance, capacitance, and the charge field effect. The ideology of the nanogap has introduced numerous signal transduction technologies in the field effect transistor based biosensor. This is the structure of the vertical nanocavity I have already explained. This is the structure of the silicon on insulator biosensor. Next is the most important process in the FET based biosensor, that is absorption. The absorption of biomolecule leads to the modification of the electrostatic coupling between the gate and the channel. After the absorption of the biomolecule in the cavity, the enhanced cavity length increases the threshold voltage, surface potential, and drain current in comparison to the air-filled cavity. That is delta VTH. It is the change in the threshold voltage when there is no biomolecule in the cavity region and when the biomolecule is introduced in the cavity region. By introducing the biomolecule in the cavity region, it will change the threshold voltage of the proposed device. Thus, the change in the drain current and the threshold voltage of the biosensing device can detect the presence as well as the orientation of the biomolecule in the cavity region. The specific binding without any label as well as the presence of the biomolecule in the nanogap, either it will be partially filled or fully filled, can be detected by tracing the change in the electrical characteristics, drain current, threshold voltage, surface potential of the proposed device. It means by tracing the change in the electrical characteristics, drain current, threshold voltage of the proposed device, we can detect or recognize the target biomolecule in the cavity region. For example, this shifting of the threshold voltage towards positive side marks the presence of the negative charge biomolecule in the cavity. The shift in the threshold voltage providing the dielectric modulated field effect transistor device sensitivity. It is a function of two facts. First, one is the charge of the target biomolecule, not in the case of the neutral biomolecule. And the second is the modulation effect of the gate dielectric. The target biomolecule can be negatively charged biomolecule species such as bacteria and DNA, or positive charged biomolecule such as glucose oxidase, or charged neutral entity such as virus and the protein. Bacteria or DNA, it is only the negative charge biomolecule. Glucose oxidase, it is the positive charge biomolecule. And the virus and the protein, it is the charge neutral biomolecule. Next is the current scenario. The advancement in the field of FET based biosensor are undergoing revolutionary changes and leading to a wide range of FET based biosensors to overcome the problem of electrochemical and optical biosensors. Although electrochemical sensors offer miniaturization, low cost, and the portability, the requirement of the reference probe in the circuit possesses problem. The optical biosensor offers label-free detection, but the operator's complexity and the expensive fabrication process has led to the development of more options such as quartz crystal microbalance or FET-based biosensor. With the growth in the technology, the improvement within the field of FET-based biosensor has led to the development of extended gate field effect transistor, dielectric modulated field effect transistor, nanowire FET biosensor, TFET biosensor, organic FET biosensor, and the organic electrochemical transistor biosensor. Next is the different challenges in device design for obtaining high performance. The FET based biosensor have shown quantitative analysis of biomolecule, high sensitivity, and the fast response. Nevertheless, great challenges remain to construct FET based biosensor for layperson with features such as miniature size, small size, low cost, portable biosensor, simple operation, commercially available, and the regenerable or reused and reliable in addition to optimized sensitivity and the stability. The major areas which demands improvement and development are show channel effects, immobilization technique, specificity, signal to noise ratio, regeneration, dynamic property of the target biomolecule. If you are designing any biosensor, you must consider these factors to improve the quality of the biosensor. First one is the show channel effects. The show channel effects deeply affect the performance of the sensing device, mainly sensitivity. Many device engineering approaches have been employed, such as gate dielectric engineering or asymmetric channel doping in case of TFET. Next is the immobilization technique. The immobilization technique needs to be chosen in such a way that the selected method should result in reliable sensor surface that has low absorption, high binding efficiency, high specificity, and the high selection of the target biomolecule. The selection of the right immobilization technique can help in commercializing cheap and efficient FET based biosensors. And the second point is the properties of the sensor surface decide the method of immobilization that can be employed for better operational stability. The next is again important factor, that is specificity. The specificity or selectivity is a characteristic that is equally important as sensitivity to characterize the biosensor structure. The absorption of the biomolecule on the sensor surface changes the device characteristics. In order to achieve high specificity or selectivity, the channel should either be functionalized directly with the specific receptor, linker, or mask with any polymer dielectric layer with same dielectric constant as that of the target biomolecule to enable the functionalization. Which means if you are using the label based reduction, you have to use specific receptor or linker which have the same dielectric constant as that of the target biomolecule to enable the functionalization. Next factor is a signal to noise ratio. It refers to the ratio of actual signal transduced from the target biomolecule to the noise signal from the non-target biomolecule. Second point is basically the signal to noise ratio reflects the fidelity and depends upon the impedance matching between the different subsystems of FET based biosensor. Next factor is the nanocavity filling area. The sensitivity and the performance of the FET based biosensor depend upon the nanogap capacity and its filling criteria. It must be partially filled or fully filled. It also depends upon the biomolecule orientation because biomolecule orientation changes the dielectric constant of the target biomolecule. Despite this shape and the size of the target biomolecule, the device analysis is generally carried out with an assumption that the nanocavity is fully filled or partially filled with target biomolecule. Next, regeneration is the important factor. Most of the sensors are of one-time use only, which limits the reproducibility as well as reliability of the sensors. The biosensor with poor regeneration ability are even less demanded in real-time application. For example, in the medical field, a biosensor that does not need to be replaced after every use is highly desirable. In order to enhance the sensitivity of biosensor, regeneration is a mandatory step. Next is the dynamic properties of the target biomolecule. The target biomolecules can range from picometer to nanometer in their length, and the biosensor it must be highly sensitive and responsive to detect even a single molecular interaction. The extensive property of nanomaterials such as high specific surface area, increased aspect ratio, and high stability can lead to the development of novel FET biosensor. The first biosensor is the ISFET biosensor. It has some shortcomings. After that, we are using the dielectric modulated field effect biosensor, but it has also some shortcomings. Scaling of dielectric modulated field effect transistor introduces various shortcomings which limit the use of sensor, such as high cost, biomolecule detection time is large, low sensitivity, high power dissipation due to the high leakage current, minimum ion-IF ratio, scaling of the threshold voltage with respect to power supply, and the various source channel effects. These factors reduce the sensitivity of the dielectric modulated field effect transistor biosensor, so that we have introduced TFET based biosensor. So that dielectric modulated tunnel field effect transistor is extensively used for label-free detection of biomolecule due to its ability to provide better sensitivity, improved response time, and the energy efficient due to low leakage, and is proficient to overcome all the shortcomings related to the dielectric modulated field effect transistor based biosensor. In this slide, we are discussing the Shortcomings of TFET and junctionless TFET used biosensor. First one is the abrupt junction profile is also a very challenging task. In this slide, we are discussing the shortcomings of TFET and junctionless TFET based biosensor. Shortcoming of doped TFET biosensor. First one, abrupt junction profile is also a challenging task. Second is high doping concentration constitute fabrication process not easy to analyze. Third one, random dopant fluctuation. Random dopant fluctuation in during the ion implantation and diffusion process, some atoms are dislocated from the position, so that a high temperature process is required to move the atom into the original position, so that the thermal budget of the device is high. High thermal annealing technique is required to move the atom into the original position, so that expensive thermal annealing technique is required in the doped TFET. And the last one is the high mobility degradation. After that, we have introduced junctionless TFET biosensor. There are three shortcomings of the junctionless TFET biosensor. Above certain thickness in doping level, junctionless TFET can latch to the on state and fails to turn off, even if you are decreasing the gate voltage less than threshold voltage. Another shortcoming is again random dopant fluctuation, because we are using the high doping concentration at the substrate. And the last one is the junctionless TFET are more sensitive to process variation, specifically thickness and the doping variation. All the shortcomings of the dielectric modulated FET biosensor, TFET biosensor, and the junctionless TFET biosensor are minimized by using charged plasma TFET biosensor. Solution with the charged plasma TFET biosensor. Charged plasma TFET are more immune to process variation. This means there is a small change in the doping and the thickness, it will change the electrical attribute of the device. Second one is the excellent control of the short channel effects. Third one is the less mobility degradation. Fourth one is the no random fluctuation, because we does not require high doping technique, diffusion and the ion implantation, so that the thermal budget of the device is low. Less biomolecular detection time, because it has subthreshold slope less than 60 millivolt per decade. Charged plasma TFET has the potential to realize at the low temperature process. Better sensitivity for the neutral as well as charged biomolecule. There is a one problem with the charged plasma TFET biosensor, that is control of the metal contact work function at the source and the drain side is a very challenging issue. Before you go to the code, first you must know how to define material in Silvaco. You can define any material using user.material in the reason statement. Reason number, specific number with the positional parameter x minimum, x maximum, y minimum and y maximum. User.material, for example, graphene. You can give any name in the place of graphene. Next is you have to define material, material name. Any name you can use. You can use graphene, you can use alpha, you can beta, you can use any name. Next, you have to define the band gap, e.g. at room temperature. Next, you have to define the affinity of the proposed material. Next, you have to define mobility of electron and hole of the proposed material. Next, if the material is oxide, you have to define the permittivity. Next, defined density of state for electrons as well as holes. Next, you have to define TAUP and TAUN. Next, you can call any index file, for example, ZNO. Next, you have to define user.group. The proposed material will belong to which group? Means either it will be insulator or semiconductor material. If the user.group is insulator, you have to use user.default. It is an oxide material. Let's go to the code. Start from the go at less. Next is the multiplying factor is 1 to the meshing. First I have defined x meshing, then y meshing. X meshing is start from the 0 to up to 268 nanometer with different spacing limit. Please note down the meshing very carefully to obtain the optimized result. Next is the Y meshing starting from the -5 nanometer up to the 15 nanometer with uniform spacing, that is 0.0005, or we can say that 0.5 nanometer. Before defining the resin or material statement, I have defined the permittivity of the target biomolecule. I have assumed that air is present in the nanocavity region, so that I have fixed the value of the permittivity at 1. You can also define the permittivity in the material section, that is this section. In this section, I have chosen the permittivity and name it as my per and fixed at 1. There is a one option is that you can choose the permittivity 1 at this material section also. After that, I have defined the reason statement with material, with different material. Reason number 1 with their positional parameter and the material is SiO2. Reason number 2 with positional parameter and the material is again SiO2 oxide material. Reason number 3 is the user dot material. I'm using the user dot material my oxide. I have given the name of the oxide in the nanocavity region is my oxide material. Reason number 4 with the positional parameter and the material is again oxide. Reason number 5 with their positional parameter and the material is silicon. Reason number 6 with their positional parameter and the material is again oxide material. Next reason is 7 and the material is SiO2. Next is the reason number 8 and the material is user dot material. And the name of the material is I had given my oxide material. The last reason number 9 with positional parameter and the name of the material is oxide material. Next, I have defined the quantum tunneling meshing. You can define the quantum tunneling meshing in the two ways. I have already explained in my previous video. If you don't know how to define the quantum tunneling meshing, please follow my previous video to understanding how to define quantum tunneling meshing in the TFET structure. Next, I have defined the electrode statement. I am using dual metal gate at the channel region. That's why I have defined gate 3 for the upper side, gate 2 and gate 4 for the lower side. Next, I have defined the source electrode and drain electrode. Next, I have defined the doping. The uniform doping is used at the substrate because we are using the charge plasma technique in the region number 6. Sorry, it is not the region number 6, it is the region number 5. Next, I have defined the material statement. I am introducing a new material with the name as my oxide material. With the user dot group is it is the insulator material and the user dot default is the oxide and the permittivity I have fixed at 1. Next is the specifying the interface property. The interface statement is used to define the interface charge density and the surface recombination velocity at the interface between semiconductor and the insulator. For example, the statement QF is 0 I have taken. You can take any value of the charge density 1E10, 2E10, 3E10, 4E10, 5E10, 1E11, 1E12 per centimeter square. In many cases, the interface of interest is restricted to a specific region. This can be accomplished with positional parameter x minimum, x maximum, y minimum and y maximum parameter on the interface statement. These parameters define a rectangle where the interface properties apply. Next, I have defined the contact drain side, gate side and source side. I am using two work function. In the proposed device, I have shown 3.9 and 4.5. but in this code I am using 3.9 and the 4.0. This is the drain work function 3.9 to induce charge carrier approximate 5E18, and the source side we are using the 5.93 work function to induce the charge carrier approximate to 1E20. Next you have to define the model. I have already explained in the previous videos about the different model used in the TFET. Next you have to save the file and you can view the file in the Tony plot. Next you have to give the voltage at a different terminal. You have to apply 50 millivolt at the drain terminal. Next you have to save the log file. Next applying this command to find out the conductance and the capacitance in the device. And the last one, you have to save the log file and the structure file, and you can view the log file and the structure file in the Tony plot. When you run the program, you will find the log file, this one. You can observe that by introducing the air in the cavity region, the value of the on current is low. When you put the biomolecule having high permittivity in the nanocavity region, the on current start increasing. We will discuss about that in the next slide. This is the structure file you will get after run the program. 3.9 work function at the drain side and the 5.93 work function at the source side. And the gate has two different work function, 3.9 and the 4.0. This is the nanocavity region. Next, this is the structure file. This is the characteristic color. The variation of drain current due to bonding of different neutral biomolecule in the open cavity region. When the cavity length is fixed at 7 nanometer at VDS is equal to 0.5 volt, in which K is equal to 1 represent the air in the nanocavity region. When the cavity is filled with different biomolecule, the value of dielectric constant increases in the cavity region. The barrier width between the conduction band of the channel and the valence band of the source increases with the formation of cavity, which result in very low probability of electron tunneling. So that if you are increases this length of the cavity, the drain current start decreasing. One more thing to note, that the on current of the device rises with the increase in the dielectric constant of the underlap region, whereas the off current remain constant, because with increase in the dielectric constant in the cavity region result in band bending at the source channel interface, which leads to the reduction in barrier width. This will start increase the on current. In the simple way, we can say that if you are increasing the length of the cavity, the drain current start reducing. If you are introduce the biomolecule having high dielectric constant in the cavity, the on current start increasing and the off current remain constant. This is because of as you increase the dielectric constant in the cavity region, the band bending at the source channel interface take place. This will increase the probability of tunneling and it also increase the on current of the device. Is the drain current characteristics for the case when the charged biomolecule are immobilized in the cavity region. The on current increases in the presence of positive charge biomolecule and decreases in the presence of negative charge biomolecule in the cavity region, and the off current remains almost constant. The reason behind is that immobilization of positive charge biomolecule in the cavity region result in decrease of barrier between the source channel interface. You can see in the figure that if you are increasing the surface charge density at the SiO2 interface, the on current start increasing because it will reduce the barrier at the source channel interface. Next is the effect of variation of geometry parameter on the device performance. Figures show that the drain current variation with respect to gate wise for different value of cavity length. As the length of the cavity is increased from 7 to 10 nanometer while maintaining the gate length constant, it is observed that the on current decreases. I have already explained that if you are increasing the length of the cavity, the drain current start reducing because it will increase the barrier width at the source channel interface. This figure shows the drain current variation with respect to gate wise for different value of cavity thickness. It is observed that the on current value of the drain characteristics start decreasing as you increase the thickness of the cavity. of the proposed device. As you increase the thickness of the cavity region, this will reduce the barrier at the source channel interface. This will help to increase the on current of the device. This is all for the charged plasma TFET biosensor device. Next, we will move to the junctionless TFET biosensor. Let's move to the code of junctionless TFET biosensor. My dear friends, this is the code for the junctionless TFET biosensor. Start from the go at length. The meshing starts from the minus 15 nanometer up to 265 nanometer, and the y-axis start from the 5 nanometer up to 15 nanometer with different spacing. Please note down the code very carefully. Before move to the resin and material statement, first I have defined the permittivity of the proposed material. Permittivity of the proposed material I have set 12 in the case of junctionless TFET biosensor. First reason, having the material of SiO2 with different positional parameter. Reason 2, 3, 4, 5, 6, all material have the same oxide layer SiO2. The reason number 7, having material silicon. The reason number 8 has proposed material user.material. The name is variable oxide with their positional parameter. And the reason number 9 is again with the proposed material with the name of variable oxide. Next, again I have defined the QT reason, quantum tunneling meshing. Next, I have defined the electrode, dual metal gate material. So I have defined gate 2 for upper and gate 3 and gate 4 for the lower. Next, I have defined the electrode name source and drain electrode. Next, I have defined the doping. The doping of the junctionless TFET is 10 raised to power 19. In case of charged plasma TFET, the substrate doping is 10 raised to power 15 with their positional parameter. Next, I have defined the material statement with the name variable oxide. The proposed material is insulator and the default is oxide. Having the permittivity, I have defined upper 12. In the previous code, I have already tell you, you can define the permittivity at this place also. You can define 12 permittivity in the material statement. Next is the interface statement. I have taken the charge density 0. Next, I have defined the contact name. In case of charged plasma, I have taken the different gate material with work function of 3.9 and 4.5. The source work function is again 5.93 to obtain the doping of 10 raised to power 20, and no work function is used at the drain end because it has the doping of high doping equal to 10 raised to power 19. Next, I will define the model statement. Next, I will define the output valence band. This is used for to find out the different valence band, conduction band, surface potential from the model file. Next, I will define the different voltage at the drain end, source end and the gate end after the method statement. After that, we have saved the file, structure file and the log file. By using the Tonyplot statement, you can view the structure file and the log file. When you run this program, again you are getting two files. One is the structure file and one is the log file. This is the log file. This is the structure file. You can check the material. I have introduced oxide material with the name of variable oxide, and the substrate doping is 10 raised to power 19. In case of charged plasma TFET, the variation is on the on current, but in the junctionless TFET, the variation is in the off current. The sensitivity criteria in case of charged plasma TFET applying at the on current, and in the case of junctionless TFET, the sensitivity criteria is applying at the off current. I will explain detail in the next figure. Again, in which k is equal to 1 represent the air is present in the cavity region. Figures show that the drain current characteristics with respect to gate voltage when the cavity length is at 7 nanometer. It is important to note that the device shows sufficiently change in the off-state current of the drain characteristics. the point at which the relative permittivity of the cavity region increases from K is equal to 1 to K is equal to 12. The threshold voltage starts reducing, which result in fall of the off-state current. The reason behind is that any type of charge carrier available in the channel moves towards the drain terminal, which results in flow of current. The P plus type source introduce less number of dominating charge carrier into the channel. This bring a very low off-state current. When the value of relative permittivity of the cavity region rises from K is equal to 1 to K is equal to 12, the off current start reducing, and as well as variation in the on current is observed. The variation in the on current is very less as compared to variation in the off current. In the simple language, we can say that the P plus source region introduce less number of dominating charge carrier into the channel. This brings a very low off-state current when the bimolecule having the permittivity 12 is introduced in the cavity region. Next figure, when the bimolecule having the charge, or we can say that positively charged bimolecule is introduced in the cavity. When the positive charge carrier bimolecule immobilized in the cavity, it will change the off current of the device. You can observe from the figure that improvement in the off drain current when positively charged bimolecule are introduced in the cavity region. When positively charged bimolecule are immobilized in the nanocavity area in the presence of neutral bimolecule by the change in the surface density from 0 to 10 raised to power 12 per centimeter square by simply changing the interface charge density, which is surface recombination velocity at interface of semiconductor and insulator layer. By simply changing the value of surface charge density, we are assuming that the charge bimolecule is present in the nanocavity region. As we introduce the positive charge bimolecule in the cavity, it will decrease the barrier width across the source channel interface, which result in fall of the off-state current of the junctionless TFET biosensor. When the surface charge density at the SiO2 interface is increases, the off current start reducing. My dear friend, this is end for today. If you have